In this question, a student follows the correct lab procedure to fill a cuvette with a 0.360 m solution and tests it in a spectrophotometer to produce an absorbance spectrum graph as shown in the image provided. Okay, so the spectrophotometer, that's shown in this image here. Again, it consists of a light source that shines light through a fluid and into a detector to determine how much of the light was absorbed by the fluid. The cuvette is this thing here. That's the plastic or glass container that the fluid goes in. And the absorbance spectrum graph shown down here is absorbance and wavelength. So what we've done here is put one sample of fluid in that cuvette, and for the light source, we've used different wavelengths of light, starting at 300 and going up to 700 nanometers. And as we change the wavelength, the amount of light that gets absorbed changes as well. And in order to get the most accurate results, we're looking for a wavelength that has the most absorption possible. So if we have a look at our graph, this would be our peak absorbance. So that's our interesting point on our graph that we're going to be using for our calculations. The first question asks, what is the ideal wavelength that should be used to measure the molar absorptivity of the solution? So that's at the point we just identified. Our wavelength is on the x-axis. So if we go down and find our wavelength at that point, it's 550 nanometers. So that's going to be our ideal wavelength. The next question asks, what is the absorbance measured at this ideal wavelength? Absorbance is the y-axis of our graph. So again, if we go from our interesting point across to the y-axis, we can see our absorbance was 0.2 at that point. So that's our peak absorbance. It's 0.2 and it happens at a wavelength of 550 nanometers. The next question is asking for the path length used in this experiment. So the path length is the length of fluid that the light traveled through between the light source and the detector. So the light is coming from this direction. It travels through our fluid and then continues on towards the detector. So this distance here, that is the distance that we care about because that's the length that the light had to travel through. So our path length is going to be 2.5 centimeters. So we can fill that in here. So we've now used our diagram and our graph to figure out all of our variables so far. Our last step is to calculate the molar absorptivity of the solution at that ideal wavelength, which we're going to find using the Beer-Lambert law. So let's go to our reference sheet. Here is the Beer-Lambert law. A equals epsilon ml. Let's go ahead and write that down. A equals epsilon ml. So the A here is the absorbance. That's what we calculated up here, and we got 0.2. The epsilon, that is our molar absorptivity. That's what we're trying to find in this last question. The M is the molarity, or concentration of our solution, which we have given in the question as 0.360 m. And the L is the path length, which is what we found here from our diagram. So we're going to be rearranging our equation to get epsilon, or the molar absorptivity, on its own. Epsilon is currently multiplied by m and L, so I'm going to divide by m and L on both sides of my equation. The m's and l's on the right will cancel, leaving us with epsilon is equal to A over m times L. So we can go ahead and put in our numbers now. A is the absorbance, which was 0.2, divided by m, the molarity, which was 0.360, multiplied by L, the path length, which was 2.5 centimeters. If we put that all into our calculator, we're going to get out a molar absorptivity of 0.222, and our units are per molar centimeters. because absorbance doesn't have a unit. And then we divide it by m and L, which have the units of m and centimeters. So that's how we get the per molar centimeters as our unit. So we can go ahead and fill that into our answer box now. So in these questions, these are the variables we're going to be working with. It's the absorbance at the ideal wavelength, the molar absorptivity of the solution, the molarity of the solution, and the path length. And in each question, you may be given different combination of those variables and being asked to find a different variable each time, but you're using the same equation and the same techniques to do that.